Great. So for our second talk, we have Eduardo Gonzalo from Madrid. He's going to be telling us about pair production and the weak gravity conjecture. So,
thank you very much, and thank you both of the organizers for giving me the opportunity to present my work in this very nice summer series of string phenomenology. So I have been working in the Swampland in my PhD thesis, and particularly I'm interested in extracting phenomenology, and I do think that this is a great time to be in our field, and I have high hopes that we will do nice phenomenology, and I hope my talk is part of the new things that can be brought about the phenomenology. So first I will start with a motivation where I will explain the relation of our proposal with the weak gravity conjecture, and once I have explained our proposal, I will apply it to a couple of situations. First of all, I will apply it to U1 interactions, where we will make close contact with the standard weak gravity conjecture. Then I will apply it for scalars, because that's the novelty, that our proposal can be also applied to theories with scalars. It's like a new way to compare the strength of gravity with other interactions. And I will explain then how this can lead to interesting phenomenology, which is the main point after all of the talk. And finally, if I have time, I will make connection by studying an example with scalars and U1 gauge fields. I will make a connection with other conjectures like the repulsive force conjecture, which also treats situations like this. And finally, I will make some conclusions and think a little bit about what can we do next. So I always like to start with this slide, because I think that it is the case that most of the Swampland conjectures that we know, we have a certain evidence of them, and we can consider more rigorous. They are less useful in extracting phenomenology. And it's true that some of them are more speculative, but the hopes of finding interesting phenomenology are huge. So I think that my talk can be in this bottom right corner. Let's see. Okay, so let's start with reviewing the weak gravity conjecture, because it's very related to our proposal, in case someone in the audience doesn't know the details. So the main argument for the weak gravity conjecture is black hole discharge. So if extremal black holes are stable, then it is possible to have a large number of them, and this is in tension with the large number of black hole remnants is in tension with holographic bounds, and it was afflicted with other pathologies. So the standard law here is to forbid stable extremal black holes. So if we want them to be able to decay, at least kinematically, for example, in a theory with a U1 N gauge symmetry, we need multi-particle states in the spectrum with charges equal to the possible charges of the black holes, and with the mass of this multi-particle state has to be such that the decay is kinematically allowed, and for only one U1, this is just simply m smaller than q, and we can think of this in terms of the Newtonian potential and the Coulombian potential. So this is just telling you the gravity is the weakest force. This is probably known to everybody. So the idea is that if the weak gravity conjecture is true, then because of dimensional reduction, some kind of the graviton gives rise to scalar fields and graviphotons. So some kind of a scalar with gravity conjecture, some version for scalars, is expected to exist. I mean, they have to appear in some kind of way. So the starting point of my talk is, let's try to think of different ways to compare the strength of gravity, like a sort of a reformulation or extension of the weak gravity conjecture, in a way that we can include the scalar fields. And we will be mostly thinking in 4 dimensions, but it might be extended to other dimensions, but let's focus on 4. Okay, so the idea here is, if you think about, for example, the electron here as the weak gravity conjecture particle, which is exchanging photons, and then you compare the strength of this interaction with gravity. This is the standard diagrammatic interpretation. So now we want to include scalar forces. So for example, we don't want to just think about long range forces, but also short range forces. So instead of this situation, let's think of diagrams where we consider massless particles exchanging massive weak gravity conjecture particles. So the weak gravity conjecture particles will be in the propagators. For example, let's think about scalar QED. So here we have photons and gravitons. I hope you can see my finger here. We have photons and we have gravitons, and they are producing pairs of particles. So we want to compare the rate to produce pairs via photons with the pair to produce it via gravitons. And this gives you this gives you complementary information regarding the strength of gravity. Now, because this is per production or annihilation, it's the same, doesn't matter. It can be related, it might turn out to be related to black hole, but we will stay with this perturbative formulation, but maybe it is even closer related to, it's like an extra requirement, like a dynamical requirement for black hole decay. But for the time being, we will not consider this. We just think that this is another way to compare the strength of gravity with other interactions. So this is the idea. We will use per production or annihilation to arrive at a weak gravity type of condition, which includes the requirements of black hole decay, but also can be applied and says something about the massless scalar mediators. Okay, so we want to make the statement. Now I'm trying to drive you into the statement of the proposal. So we will try to keep it as close as possible to black hole extremality. So for example, if we apply our principle of pair production to a theory with multiple U1s, we want to get the convex Hall condition. Now, there are other complementary approaches to what I am trying to do today, like the repulsive force conjecture, which also tests the strength of gravity in some way. But it doesn't, and you can include scalar field, but it doesn't provide you a purely scalar with gravity conjecture in the sense that it cannot compare two attractive forces. So all of these approaches are complementary, and let's just see and compare them later on. Okay, so let's start with because like I said, I want to, in the case of multiple U1s, I want to get the precise statement of the weak gravity conjecture. So just in case someone in the audience doesn't remember it, I will very quickly review it. So we want to make sure that extremal black holes can decay. So here, extremal black holes are black holes with no negative singularities. Sorry, the subextremal black holes are or here, and this is the boundary in gray in this picture. So we want to make sure that all of the extremal black holes can decay, and they will decay to superextremal particles along the rational direction. So here we are plotting the charge over the mass. We have two charges, two U1s, so the plot is two-dimensional. We have three fundamental particles in the spectrum. I mean, this is just an example. These three particles and the corresponding antiparticles. And what's drawn here is this convex region is the convex Hall generated by these particles. So extremal black holes will decay along the rational direction because charge needs to be conserved. And we want to make sure that they can decay, okay? So the point is that the multi-particle states are all of these dots are multi-particle states. For example, this black dot here is a particle 1 and an antiparticle 2. So the mass is the sum of the two particles and the charge is given by this formula, and so on. All of these are multi-particle states. So they populate the convex Hall. So the point is that we need the convex Hall to enclose the black hole region, because in this case we are certain that there will be a black hole. There will be a multi-particle state towards which the black hole can decay. So we can formulate this in a precise way in this statement. So that for every rational direction in the charge lattice, there is a superextremal multi-particle state. This was just taken out of the repulsive force conjecture paper, and this is very close to the statement that we will make. Of course, this is the standard weak gravity conjecture, which does not behave well under dimensional reduction. So it can be extended to a tower and a sublattice version, and our proposal will also be easily extended to these two versions. And the novelty is that here there's not one, but infinitely many particles that you require. Okay, so the diagram we need only one final ingredient. We need to compare the interactions at a certain scale, at a certain energy scale, because we have short range interactions, long range interactions. So the rate for producing the pair of particles we want to compare the rates at a certain energy, and then the natural energy for a certain pair for a certain weak gravity conjecture pair is the threshold energy. So the energy from which you can generate the pair. So which is the energy scale of the state. So the statement is for any rational direction in the charge lattice, and for every point in moduli space, we conjecture that there is a stable or metastable particle whose pair production rate by gates and scalar mediators at threshold is larger than its graviton production rate. This is the idea that I have been driving you to, just put everything put together, and this is just the equation showing it. So this equation, different from the standard weak gravity conjecture, or the Repulsive conjecture, is a purely quantum relativistic. It does not reduce to a classical non-relativistic potential. So these are the diagrams that I showed you before. So what we need to do is just introduce Feynman diagrams and compute the rates. So we do it for a scalar QED. The computation for gravitons is a little bit harder, but we borrow it in the literature from papers about quantum scattering using crossing symmetry. Anyway, you do the computation. At the end of the day, what you get is this equation right here, which is the standard weak gravity conjecture. You can do the same for fermions, and you obtain the same. So far so good. We have been able to recover the extremal black hole bound, and it is the same as the weak gravity conjecture. If we do it for multiple U1s, the extension is very simple, and you get the convex Hall condition. And in fact, we can make our statement even closer to the weak gravity conjecture kind of statement by defining a state to be superproduced if the rate to produce this pair at threshold is larger or equal to the rate to produce that pair from graviton. So in the weak gravity conjecture, we talk about super extremal particles, which are particles which are outside the black hole region. And in the pair production, we talk about particles which are superproduced, which are particles that the rate to produce it is larger in any other interaction other than gravity. So for every rational direction in the charge lattice, there is a metastable particle which is superproduced. Okay, this is the statement. Now, black hole arguments do not care whether the state is single or multi-particle state, but in the pair production, we actually care. It has to be a particle in the pair that we produce. So in this sense, it is closer to the stronger statements of the weak gravity conjecture, which behave well under dimensional reduction. So we might as well conjecture from the start a tower or a sublattice version. For example, the tower version will tell you that for any point there has in the charge lattice there has to be an integer n where there is a particle. So you conjecture infinite particles. Okay. So I have explained you our proposal. We have seen that it gives the same results when you apply it to situations with U1s as the weak gravity conjecture. Now let's do something new. Let's apply it to a situation where we have scalar fields. So let's consider a heavy state H, which can be the state of any excited state of the string or Kaluza-Klein state. And let's consider some moduli, which I call T here, and the mass of this heavy state is a function of this moduli. And let's consider the rate to produce this heavy state starting from 2 moduli and compare it with the rate starting from 2 gravitons. Okay, so this is the diagrams that we have to compute. We introduce the Feynman rules, and what we get is this equation, this inequality. We have absolute values because we're talking about a rate. The generalization to more moduli is simply given by this equation. Now, a similar equation was actually proposed by Palti in 2017 based on an identity in n equals to supergravity, which is essentially the same as this, but without this absolute value, which comes from the rate. So immediately this guarantees that the equality sign here, so the states, the n equals to BPS states will be saturating this bound. They will give you an equality. So this is a nice result. This is what you would expect. But the additional thing is that since we have an absolute value here, if we take the Planck mass to infinity, And unlike other versions of the weak gravity conjecture involving scalars, the condition becomes trivial. And this is something new and something that is interesting because this is positive. So it just becomes trivial. So it seems like it's like purely Swampland, like something that's actually related to quantum gravity. More interesting things about this inequation. If you study saturating solution, so you take the quality here, and study which kind of objects can follow from this equation, and so the m squared will be positive, and you can just write it as an exponential of a function f. We introduce this in our equation, and what you get is this. So if there's a state with mass m that is saturating the bound, then a state with 1/m squared will also saturate it because of this duality f minus f that follows from the rate. So the point is that the saturating solution, so the states, the BPS-like or KK or winding states, they have built-in duality symmetries. So this is just something that we impose on the effective field theory, but it has like a stringy taste because it has built-in duality symmetries. This is also something that has been very interesting. We have tested the equation here with towers of BPS particles in type IIA Calabi compactification with particles that come from DP branes wrapping even cycles, and they also saturate our bound. We need more evidence, but we have been making some tests. Okay, so now we have seen how the proposal applies to scalar fields. Now let's see how we can get some phenomenology from our proposal. Because the obtained bounds, as if you have followed me, you know that they apply to a string excited state, to weak gravity conjecture states, coupled with mediators in the massless sector. But these states are very massive. I mean, maybe except in asymptotic limits of modular space, they are very massive. So the question is, can we find constraints on massless or nearly massless scalars with an actual relevance in particle physics or cosmology? This is the question. So there are two ways to do it. The first one is think about moduli. So they are massless in principle, but they can get masses from loops of these heavy particles. So if this is the case, then maybe the mass of the moduli gets a dependence on the masses of the heavy particles. So the mass of the heavy particle is constrained because we want gravity to be the weakest force. So we have a constraint on the mass of this heavy particle. And if the moduli mass is getting a mass from loops of the heavy particle, then it will depend on the mass of the heavy particle. So from this dependence, we can indirectly put constraints on the mass of the moduli, and in this way do phenomenology. So this is one possible way. There's another way which is stronger. That's why we coined it the strong scalar weak gravity conjecture, where the moduli themselves acquire a mass that obeys the same constraint. So we think that the moduli, they get a mass for whatever the reason, and we also say that the self-interaction of the moduli itself, it has to be stronger than gravity. So then the mass of the moduli has to fulfill the inequation. So we can substitute m squared with the second derivative of the potential, and that's how you get this kind of equation, which is similar to a strong scalar weak gravity conjecture that we published last year. But there's something new here. It is better motivated. It comes from a general principle, which also includes the convex Hall condition and all of the other nice things about the weak gravity conjecture. And the novelty here is that because it comes from rates, it has this absolute value. So again, it is purely Swampland in the sense that when m Planck goes to infinity, this is always positive and there's no constraint. So the idea is just, okay, so we apply this to different potentials and extract phenomenology because this has to be true. So first of all, we can apply to an action potential because there was another proposal to do this without this extra term. So if you don't include this fourth derivative, then this potential would be in the Swampland, but with this new term, so just as it is here, this potential is fine as long as the decay constant is more than the Planck mass. The next test is a Higgs-like potential, of course. So if we consider this potential and we just plug this in here, we get this inequality. And if it didn't have the absolute value, you can see that it would be violated. And this will, sorry, so here, you just, it would, if it didn't have the absolute value, it would be violated when phi is equal to 0. And this would happen if this goes to 0. So in this case, what we are saying is that the repulsive case would be in the Swampland. So we can run into trouble. And based on this observation, there was a paper a few months ago with provided counterexamples. So it said that this situation could not happen. But these counterexamples, they are solved, they go away when we include the absolute value. So this strong scalar with gravity conjecture, I mean, as far as I know, there are no counterexamples, as far as I know, Okay, so it will also be interesting to generalize it to the more realistic case of the standard model. We can obtain interesting phenomenology, but by doing this. For example, the lambda parameter, when we include the running, we know that it goes to 0 at this high energy scale in the standard model. And this would mean that scalar interactions become weaker than gravity. So this would signal new physics at or before this scale. This is also interesting. We can also apply to other potentials. For example, we can apply to compactifications of the standard model and try to find bounds. I will not go into these details today. I will just give you one more example before my time's up, which is the KKLT, which, and interestingly, for the ranges of parameters where we create a de Sitter vacua, the KKLT model is fine. If we change the parameters, then we can find violations, but for the ranges of interest, it is fine. But in the same way, we could test many other examples. So let me just say a couple of few words about this before I finish. So if we can think about situations where we mix, so we have seen gauge fields and we have seen scalars. Now the next thing is, okay, well, let's put them together and study what happens. And I will not go into details of it today, but it is an interesting thing that we're working on right now, because, okay, so we have the weak gravity conjecture, which was rated to extremality bound. The repulsive force conjecture, which is forbidding gravitationally bound states and is determined by an non-relativistic potential. And we have the pair production with gravity conjecture, determined by, well, you know, the diagrammatics of pair productions. We have three conjectures that can be applied in this situation. So the natural question is, do they coincide under some circumstances or assumptions? And this is a hot topic right now. Naomi was talking about this last Tuesday, about the connection between these two. So I think it would be interesting for the future to also study the connection with the pair production in some stringy construction. So what we argue in our paper is that not only the pair production of moduli has to be larger than gravitons, but when we have also photons, the pair production of states via photons has to be larger than the combined rates of producing the state via gravitons and moduli. This is our proposal, but I'm running out of time and I will not go into more details. We leave for further study, taking new stringy examples and trying to test whether these three conjectures are the same in some cases or in some situations. Okay, so the summary, I have given you the first direct derivation of a scalar with gravity conjecture from a general principle that also includes the convex Hall condition, is purely Swampland, and like other versions, the precise inequality depends on the Lagrangian. For example, it independent on the metric in moduli space, and saturating solution. So when you take the equality, they display duality symmetries. And this is related to the absolute value of the rates. So for the future, this is my last slide. The connection with the weak gravity conjecture is under study. Perhaps the pair production is also related to black hole discharge. I mean, maybe it's an extra dynamical requirement when you think about the specific way in which extremal black holes decay, like via Schwinger pair production. And it would be interesting to learn more about this. And it will also be interesting to perform the same type of computation that I have explained to you today in backgrounds other than Minkowski. We have also made some tests, but we need further testing in different extreme compactifications. And it would also be interesting to think what would happen if we include non-abelian gauge groups. So comparing the strength of gravity with the strength of non-abelian gauge interactions. And this is all that I had to say today. Thank you for watching. If you have some questions.
Great. Let's thank Eduardo again. And if there are any questions, could you please say, I have a question in the Zoom group chat. While we wait, I have one about the scales at which these scattering experiments are happening. So what momenta should I think about?
So the idea is that we want to compare the interactions at a certain scale. So we are producing pairs of particles. So the scale at which we evaluate these rates is the threshold energy at which these particles can be produced. So if you are producing a particle Kaluza-Klein state, then you would have to evaluate things at the state of the energy, at the minimum energy required to produce this state.
Okay.
I am not sure if I cannot see the faces. Oh, okay, here, yeah, I could see faces. I don't know if there are questions in the chat or something.
Hi, I have a question.
Hi.
Yeah, so from my understanding, suppose that in a string theory setup, you have a large number of moduli fields. So this bound would mean that basically the more moduli fields you have, and the coupling between the moduli field and the scalar field has to be weaker. So that's what the bound means. So somehow there's this inverse correlation.
Yes, the number of moduli it appears here. This n actually depends. So I mean the point here is that you cannot compare the strength of any number of any number of moduli with only one graviton unless you introduce some factor, some average factor to compare it. You know. So actually we actually do this so that the comparison is fair. And for the case of n equals to supergravity, this is equal to the number of vector multiplets, because that's what appears in the identity. But the point why we include it is precisely what you said, that it is not fair to compare the rate of producing a pair of particles with only one graviton and with any number of moduli. So that's why it's included here.
Well, I thought it's a sum of all the moduli field you could have. Somehow it's a 1/n, I see. There's an average thing.
Yes, exactly. So we are summing over I and j here. So over all the moduli, and then we are dividing by the number of moduli. So it's like an average. Yeah. So the comparison is
I see.